Hello, everyone. I hope you can hear me. Okay, so our next talk, I hope we all like learning, but now we are going to see how we are going to do the deep learning. Thanks to Rafael. Okay, so this talk is here. Don't forget to vote or ask questions on our bot so we can ask them after the talk if there is a time. And of course, enjoy the talk.
Thank you. We don't have the screen. Can you? Okay, thank you. Sorry about that. Artificial intelligence have been all around the news lately, and I mean they talk a lot about it, and it sounds like sometimes it's scary, sometimes it's hopeful, but you know, sorry, yeah, okay, bit of glitches with the technique. Okay, so sometimes it's like sounds really cool, sometimes it's sounds really scary. I'm pretty sure you have heard about Elon Musk warning people about the dangers of AI, but my sense has been that people just don't understand what this technology is all about. So the reason I came here today is basically to show you what deep learning is and why you should learn about it. So what you can expect from this talk. First of all, I'm going to show you how to create a deep learning architecture that will recognize numbers, handwritten numbers. That's a pretty simple task. But if I were to ask you if you could do that, probably most of you would say no, not yet. And by the end of this talk, you should have a vague idea of how you should start doing this. And the other thing that I want to make sure is that you have a good understanding of what this technology is good for and what it's not good for. So that when next time you read in the news that DeepMind had a huge breakthrough and the singularity is within 2 years, you can spot it out as bullshit. Okay, so yeah, that's the plan. Sounds good? Okay. So first of all, what can deep learning do for us? Well, here's the basic concept. Let's imagine that we have an image of a person, and what we want to do is write some code that will create a bounding box around the face. So my input is an image of a person, and my output should be 4 numbers that define a box that contains the face, right? And just the face. So put your hands up if you're a programmer. Yeah, most of you. Now keep your hands up if you know how to write this software. Yay, a few of you. A few hands went up. Okay, so the purpose now is to show you how you can do that, okay? Um, so what goes in the middle? That's the real question. And here is our plan. What we are going to do is instead of taking one image, we are going to take hundreds and hundreds of thousands of images, or even millions of images. And for each of those, we are going to define the bounding box. How you do that? Well, for example, you could either ask people to do it for free, like Facebook does, and or did back in the days. Or the other thing that you could do is you could use Amazon's Mechanical Turk, which is basically an API through which you can send in tasks, and then some chap will manually perform the task. And basically, it's for simulating AIs. Okay. So we have these two data. And what we are going to do is take both of them, feed it into an algorithm that we are going to look at today. And that algorithm will spit out another algorithm. And that will do exactly what we want. It will take the images and the bounding boxes and learn how you can take an image and define the bounding box. So in the end, we have an algorithm. That's the plan. I'm going to take this off. Just a second, because... no, I'm not going to take this off. Okay. So, what you can do with this, you can, as I said, you can create bounding boxes, but you can also classify images. So, for example, here you can see cargo ship, and it actually correctly identified it. But also there is a Dalmatian there with cherry, and it couldn't decide which one it is, so it went with cherry. Then you can colorize images. And I find this really, really interesting, because what you see here is that this information, this color information is lost, right? And we can recreate that using a deep learning model. And there is actually a website, I encourage you to try it out, where you can upload your black and white images, and it will recolorize them. And the way it works is just guesses what it sees on the image, and it makes an educated guess on what color that thing is, and then just fills it up with color. But while we are talking about lost information, I'm pretty sure you know CSI or some similar detective show where they would shout zoom and then enhance, and the image would suddenly be clear. Now the thing is, this is actually an image that I enhanced like that. So this is not science fiction anymore. That's reality. Of course, we don't regain information, but what is happening there is that it looked at the images and figured out what it sees and filled it up with meaningful generated data. So that's all fine, but let's look at some of the things, at least one example. So we are going to do an image recognition using deep learning from scratch, okay? So here is our task. We have images of handwritten numbers, and what we want to do is we want to generate a digital number, what that thing is, okay? So we will have two tricks that we have to deal with. The first one is that we are not going to tell which number it is. We are going to tell how likely a certain number is. So if we feed in a 105, it would return, yeah, I'm 99% sure this is a 5. In fact, it will tell you even more. It's going to tell you for every single number how likely that number is. So for example, here we are 99% sure that it's a 5, but there is a 1% chance that it's actually a 6. And this array is basically, this is index 0, 1, 2, 3, 4, 5. So if this is a 5, then here we should have the largest number, right? So that's the plan. And what we are going to feed the algorithm is we are going to feed the numbers, and we are going to feed an array that says, I'm 100% sure that this is a 5. That's going to be our data that we are using. Trick number 2. It's basically image filters, a very special kind of image filter. It's in every single Photoshop. Put your hands up if you have used Photoshop. Yeah, so do you know the filter, for example, emboss? Right, that's one of the none of the filters there. And actually, also unsharp mask and Gaussian blur, these are pretty ubiquitous in almost every editing software. And these are all a special class of filters called convolutions. And I'm now going to talk about what are convolutions. So this is going to be the definition that I'm going through now. So here we have an image, and what we are going to try to do is create an image detector. Sorry, an edge detector. So there is our 5, and we want to find the pixels on the edge. So the way we do that is we are going to take one 3x3 part of the image, zoom into that. We have numbers there, right? Every image is just an array of numbers. And then we will use a so-called kernel. Now this kernel, I'm going to tell you this time that this is the right kernel to use. But the trick is that most of the time we won't know what the kernel is, and we will ask a software called Keras to find that kernel for us. But for now, we know what the kernel is. And let's see what we do if we know the kernel. Well, we are going to take two numbers, the ones in the corner, and we are going to multiply that and write it into the result. Then we take the next two numbers, multiply that, write it into the result. And then we go through each and every one of those 3x3 and multiply the two numbers. And after that, we just take the result and add them all together. And that results in a single number. And that single number is going to be 1 pixel of our result image. And then what we do, so we actually created, from a 3x3, we created 1 pixel. And then what we do is we go through the entire image for every single 3x3 box and find the result. And if we do that, then we have a pretty nice edge detection. And then here's the question. What if we don't know what kernel we have to use? So this is another one. This will detect the edges on the left. This is just the left side of edge detection. But we don't know what the kernel is. How can we find it? Well, what we can do is, instead of using numbers there, we can just tell that these are variables. And if those are variables, then I can create a mathematical expression like this. This is like we multiplied the corresponding numbers with the corresponding variables, added it all together, and it should be equal to the result on the result image, right? And then I can take another 3x3 and get another equation and another one and another one. Now these are pretty complex equations, but in their formality, they actually look like this. This is a simpler version of the same equation. And you have learned at school how to solve this kind of equations, right? This is just a two-variable system of equations. And now what we can do is say, these are basically the input pixels, and those are the outputs. And all we have to find are these x's and y's, and that's going to be our kernel. And if we actually, yeah, we have to find those, right? And if we actually do that, then it turns out that this filter is all zeros except for the 1 and the -1, like this. So let's recap what we have done here. We had an input image and an output image, and we have taken samples from both images, created equations based on that, and then we solved those equations for x and y and so on to get a kernel. And that's deep learning for you. Well, not just that. It's a bit more. Because there is a problem. One convolution is not enough. It's not going to solve a problem. So we are going to use lots of convolutions. So here's what we will do. We take our number 5 image, and we are going to create 10 convolutions. And for now, we don't know the kernel. That's very important. At this point, we don't know. We are going to learn it in the future. And then, after that, we want to take another set of convolutions, the convolutions of these images. But the thing is, if you take the convolution of a convolution, that's just a single convolution. It's equivalent to another convolution. So that's not enough. We actually have to use another filter from Photoshop. And this is actually from GIMP, but it's the same thing. We are going to use this curve to change the values in the image. And this is basically adding contrast to the image, right? This is just contrast. And what we do then is that we take all those convolution, add contrast, and after that we can take from all of those images we can take another convolution. And these are actually 7 by 7 convolutions. So we are losing resolution. By this time, the first image was 28 by 28, then it was, how much was it? I don't remember. Anyway, so this is a lower resolution, but now we can add these all together, and then we get another image. And then we can do that 10 more times, and then add contrast, and then do another convolution. These are now 16 by 16 images. If I take a convolution of 16 by 16, all I get is a single pixel, right? So not just that. So we have basically done a ton of convolutions here, a lot of them, and it's a really complex mathematical expression at this point. But I want to call your attention to the last line. These are 10 one-pixel images, which is effectively an array of 10 numbers, right? And this array of 10 numbers has a number that is the largest. And that largest number happens to be at index 5, okay? And this is how we are going to use this. We are going to feed the image on top of this network. It will flow through, and what we expect is at the bottom, the brightest pixel is going to be the one that corresponds to our number. So now that we have that, so this is what we got basically, an array of 10 numbers. Now that we have that, we can use Keras to define this computation, because right now we have like this complex mathematical equation with lots of variables, and what we need is a tool that can solve those equations for us. And what we have to do with Keras is first define these equations. And we are going to do a sequential model because we are doing a sequence of operations. And the first operation was, if you could recall, a convolution, a 7 by 7 convolution, and 10 of them. That's why I have a 10 in front, and then 7 by 7. And then I also have the input shape, which is 28 by 28. And then we did a contrast, right? It's in deep learning lingo that's called leaky ReLU. For reasons why it's called that, I'm not going to go into that. But then we can add another convolution, another leaky ReLU, which is, of course, the contrast, and then the convolution. And finally, we just tell Keras that it should treat these numbers as an array, and add another function called softmax, which will essentially just make sure that all of these numbers are between 0 and 1, and they add up to 1. That's all it does. And once we have this model, then we can say, please compile this model. This just means that it will copy the whole thing onto the GPU because it's much faster to execute there. We also have to define a few variables, like what algorithm it should use. And then after that, this is the learning part. This is where the learning happens. When I call fit generator, I'm telling Keras to, hey, here are a lot of images and a lot of results. Figure out what the correct kernels should be. And the train generator is basically just a generator that will return image and result pairs. That's all. Okay? And then what we do is we do model predict, which is using the model. So at this point, when we had the fit generator, now we are ready. Our software is complete. What we have to do is just use it to predict results. And it will get about 92% of the numbers correctly. It will make mistakes, 8% of them, but we are already at the point where we actually have this network and it's functioning properly, or more or less properly. But if you play around a bit, and this is where I have to emphasize, there is no one good solution to this problem. You can come up with hundreds and hundreds of different good solutions. You have to experiment, and after I experimented a few hours, I got to this result, which is a bit more complex version of the previous one, and that actually gets 99% correctly. Okay, So this is the part where it becomes experimentation. Okay, so now we have our number recognition software. If you don't get it now, don't worry. The thing is, most of the people I talked with and are working with deep learning right now didn't get it the first time around, and not even the third time around, because it's like it's not complex, but when you actually get it, yeah, you have to get it, and you have to go through it a few times. But I'm gonna give you a great resource where you can actually listen to a very good talk. It's not even talk; it's a course on deep learning, and it's pretty long, and it explains everything in detail. What my main purpose was to give you a vague idea of how this is done. So don't worry if you don't get the details here. Okay, so now we have this technique, and what can we use that for? Well, this same technique, the same ideas that I use now, you can use that to create an AI that can sort cucumbers. And someone in China actually did that, and they built like a cucumber sorting machine. So they just pour in the cucumbers and sort it according to quality types. And that's really cool, I think. But what's even cooler, there was a guy, and I don't remember his name, and I don't have the speaker list right here, but what he did was he realized that on eBay, if you buy unsorted Lego, it's much, much cheaper than if you buy sorted Lego. So what he did was he created this machine that would pick pieces from an unsorted bucket, and then take a photo of each of them, use the neural network to decide which bucket it should go into, and then it went into the right bucket. And he sorted, I think, 10 tons of Legos like this. 10 tons, and he made some money on it. So this is the kind of stuff you can do, right? And it's like something you can learn, but to get to this point, it took me about 2 weeks. Yeah, it's not like immediately. I cannot get you there in this talk. But if you put in like 1 hour every day, in 2 weeks you will be able to do this. It's really like something you can make at home. Or you can create something that will detect on X-rays cancerous parts. So this is an actual thing that they do now, that they ask an AI to tell if an X-ray contains a cancerous problem there. Or you could say, take a photo and ask this neural network to tell you what pixel belongs to what kind of object. This is called image segmentation. And you can imagine how useful this can be, right? When we are talking about autonomous vehicles, right? Self-driving cars, they can actually take the camera and the picture from the camera and just tell the computer which pixels belong to what kind of object. So it would recognize a human or a car or whatever. And the only difference here, may I note, is that when we did our previous example with image recognition, we reduced the resolution. But you can do the same thing without reducing resolution. And you use the same convolutions and contrast curves that you would do with image recognition. It's just using it differently, okay? And then, of course, AlphaGo has made the news quite a number of times by now by beating the best human players at Go. Now, here's how it works, and it's really interesting. Of course, I'm going to leave out a lot of details, but this is the basic general concept that they were using. They take this board and treat it as an image. And when they treat it as an image, what they can do is they can create a network, a deep learning net model that will tell you if black is more likely to win or white is more likely to win. Okay? Just by looking at games that humans played against each other. And when you do that, then you have one network that will tell you, is this a good state for me or a bad state for me? And then you use another network that will take an image of the board, and it will tell you which fields are most likely to be occupied by the next move. So you have two networks. One is going to tell you what fields should you look at all, and the other one is telling you the result of that move would be good or bad for you. And then what you do is you just do a search. You look at the 5 most likely, and then the 5 most likely counter moves, and the 5 most likely next moves, and so on for like 3 or 4 steps. And after that, you look at the value network that will tell you if the result is good for you or not. And you just search a small portion of the game tree. So that's how you create a Go player. Pretty neat, right? So while we are at using multiple models to solve a single problem, I want to talk about another interesting class of models called generative models. And so the models that I have talked about so far are great for turning an image into some data. But what if we have data and we want to create an image? The other way around. How do we do that? How many of you have seen the movie Catch Me If You Can? Okay, great. So if you remember, Caprio was playing a person who is counterfeiting checks. So it's like, yeah. And then Hanks was playing the guy who was trying to catch him, and he was coming up with ever more elaborate ways to create these counterfeit checks, and Hanks had to come up with ever more elaborate ways to find which ones are the counterfeit checks. And the thing is, if you have that, so if you do that with networks, you can do something similar. So what we would have is you have one network, and you give this network the task of generating from a random set of numbers, generating an image that looks like a handwritten number. And then the other network would try to decide, is this a handwritten number or is it something that was generated by that other network? And then what you do is you train them side by side. You first train the so-called discriminator. The discriminator is one that trying to tell which one is real and which one is fake. So you train the discriminator, it will get good at telling which ones are real, and then you train the generator to generate images that fool the discriminator. And then you train the discriminator again, generator again, and so on. You train them a lot of times back and forth. And first, the generator will come up with images like this. These look nothing like numbers, right? But if you do that for enough time, it will come up with images like this. And some of those are actually numbers. And even the ones that are not numbers, you can imagine that a medical professional would write numbers like that, right? So that's an interesting thing, but with numbers, it's not that interesting. But what if you could generate images like this? So all of those are me, modified by an application called FaceApp. And there I have one smiling. I didn't smile on the photo, may I note. And then there is an old version of me and several female versions. And the way that works is you have one neural network that will tell if it sees the same person, and another, so it gets 2 photos, and it has to tell if the 2 photos are taken of the same person. And there is another network that will decide if the person on the image is, say, a female or not. And then the third network is going to try to fool both of these networks. It's going to try to fool the network that decides if it's the same person, and at the same time try to fool the network that decides if it's a female or a male. And then you get images like this, which I find really, really cool, if you think about it. Okay, this is another interesting example. How many of you know Prisma, the Prisma app? Yeah, quite a few of you. Okay. So Prisma does this. You take a photo, and then you can say, I want this photo painted in Van Gogh style. And it comes up with this. And the way it does that is, well, you actually have to take an image recognition network and play around with it a bit. But the end result is you have one network that can decide if the thing on the picture is the same thing as another picture. So if the content is the same, and the other network is going to decide, is this in the style of Van Gogh or not? And then there is a third network that is trying to fool both of them. It's the same pattern, right? And this is what you get. And this is pretty convincing, right? This is made from a photo, and it does look like Van Gogh. And finally, I just want to talk really briefly about another area where deep learning has been used extensively, and it's natural language processing. So just two examples. I'm not going to go into how they work, just to give you an idea what you can work with if you do an actual course on this. So for example, there was a network that was trained to read the text, the description or a review, read a review of a movie, and then decide that same reviewer how many stars it would give to this movie. So basically, it can decide if it's a positive review or a negative review, which I find really interesting, because if you think about it, it has to recognize sarcasm, and that's really hard problem if you try to do that manually. But these networks, you just throw at them a lot of text and a lot of ratings, and it will decide what's going on. Another example is Siri. The way you recognize what people say is by similar neural networks. Yeah, and that's all I wanted to say about all these topics. But I want to call your attention to this course. It's course.fast.ai. And it's about 20 hours of video and a lot of exercises. And if you want to find out how you can do this, I encourage you to watch those videos and play around with this whole thing. My story is I started learning this like last January. And I already can build pretty awesome stuff with it, right? And even after a few weeks, we will find out that you can build pretty awesome stuff with these tools. So I encourage you to go to course.fast.ai and learn about it more deeply, because this is an awesome technology, but it's not magic, right? So don't think it's like going to be the singularity in 2 years. Okay, finally, just two more things I want to say. I do a workshop called Lean Poker, where you can learn about how you can continuous deploy and some other methods. And I also have a YouTube channel called Morning Commute, where I drive around town with other software professionals, and I discuss interesting topics. If you want to, you can check it out. And that's what I wanted to talk about, and I still have a lot of time, so you can give me questions, I guess. Oh, yeah, and one more thing. I was just told by Mr. Parnas that neural networks weren't invented in the 1970s. They were around in the 1940s. I didn't know about that, but guess that's a nice thing that he told me that. Thank you. So are there any questions? No? Oh, one question there. Okay. Mr. Parnas has a question. No, there's no sound. Yeah. Okay. Can you try it now?
Hello? Yeah.
Hi. Okay.
You've done a good job of showing us things that these networks can do. What you haven't said, I didn't hear it. Excuse me, what you haven't said is, why are they the best way to do it? Is there other ways to do it? Are they a good way to do it? How do they compare with other methods? Because when I went to school back in the Stone Age, they still had convolution and techniques like that, and we used them for signal processing. So what's better here?
Yeah, so basically, here's the thing. Deep learning is good for stuff that you have no idea how you would do by hand. If you have a vague idea of how you are going to solve a problem by coding it manually, you are probably better off doing that because yeah, it's a lot of experimentation. It's hard to do it if you don't know the actual problem well. So my advice would be if you have a problem at hand where you have basically no idea of how you get started with the problem because it's like image recognition or voice recognition or even like self-driving parts of self-driving are like that. You can try this route. It's not good for everything. The other question or the other point there was that back in the old days we already had neural networks and they wasn't really useful, right? And what changed are basically two things. One is three things. One is a lot more data, a lot more computational power, and a few new ideas that came out in the early 2010s. So a lot more data is important because to teach a neural network like detecting bounding boxes, you need millions of images, right? And back in the old days, you wouldn't have that kind of even you couldn't even store that amount of data, right? The second thing is that you need a lot of computational power. You cannot even do this on a CPU. You actually need a GPU for having a reasonable time frame for training. And actually, you can even you can either use Amazon's GPU instances for training these models, or you can buy a GPU yourself. Either way, it's working. And the third thing is back in the old days, everyone was using so-called sigmoid activation function, which has the problem of disappearing derivatives, which I'm not going to go into what that means. But the point is that they were using the wrong activation functions, and now we have a better idea of how to build up these deep neural networks. So these are the main points I think that changed. Did I answer your question?
Halfway.
Okay.
All those things that changed, like faster computers and more data, change for every other method you might use too.
That's true, but the thing with neural networks is that they thrive on data. So for writing your own code manually, what you do there is you come up with a solution, and you don't need examples of results. You only need the inputs, right? And that's a big difference. And you don't have to come up with a big data set up front to write a piece of code that does a certain job. With deep learning, it's different. You actually have to come up with a lot of data up front, and you have to manually tag images or manually select bounding boxes before you do that.
But I can use statistical methods to do these jobs.
Yeah. Okay. Oh, I see what you mean there. Okay. So there are other machine learning methods, and those are useful for other things. Like linear regressions are great. They are basically a much simpler version of this concept. There are random forests, which are another technique. The main difference, I think, is that random forests are good for one class of problems, like these are classification problems as well, but a special kind of classification where you have like numerical data coming in on only a few fields. Linear regression is good when you have linear correlation. So these solutions are great for simpler problems, but when you have like a complex problem, then you might want to use deep learning. And actually, for simpler problems, using deep learning is overkill, and usually you end up overfitting your data. So yeah, you actually want to learn a bit about those techniques as well once you get the hang of machine learning.
I would reverse the order.
Okay. Yeah, I did it this way, but actually I did learn about other methods by now, and yeah, they are useful as well.
Another question from the bot. Can you apply to document data extraction like Excel, PDF?
Document extraction. Okay. So
Document data extraction. I mean, data from the...
Okay. It depends on what you mean by that. If you mean you want to just give it XMLs and then the extracted data, I'm not sure if that's possible. The reason is that these formats are usually compressed, and one of the things that deep learning works well for is like continuous changes. So, for example, if you have an image and you change a few pixels a bit, it's gonna be basically the same image, right? But with XML data, especially if it's compressed, finding decompressing that is not a continuous operation. And one example I want to touch on here is why isn't this screwing up security? Because we have all these public key encryptions like HTTPS uses, and you would think that now that we have deep learning, then we could say that here is the here is the original message. We create an encrypted message, and then since we know the public key, we can generate a lot of these pairs, and then we can figure out the algorithm the other way by feeding the data backwards to the neural network. And the thing is that the reason it doesn't work is because all of the encryption methods are non-continuous. They even if you change a little bit, it's gonna screw up the entire data, right?
Thanks. Any other question from the audience? What was the language used in the...
Yeah, it's Python, and actually I was using a library called Keras, which is a wrapper on top of TensorFlow, which is a deep learning library by Google. And the reason I used Keras because TensorFlow's API is not that good, or it wasn't that good. By now, they actually hired the guy who did Keras, and they just integrated Keras into the new TensorFlow. So if someone wants to try deep learning, I guess TensorFlow or Keras is the best choice.
Thanks. Any other question? Okay, thank you.
Thank you.
Lepsze jest.